Thank you for joining us today. You're here to find out if you're missing a data frame, I take it?
Is anybody missing a data frame?
Well,
Don't know.
yeah,
right,
too soon,
right.
too soon. We will tell you about data frames, specifically in Java, what they're good for, how they can be a missing element of your data-oriented programming toolkit. But before we start, just a very quick introduction. My name is Vlad Zakharov. I've been coding in Java for over 20 years now. And also, I was a member of the GSR 335 that delivered Lambda expressions for Java. If you recall, they were released with Java 8. And I served on the Java Community Process Executive Committee for a few years. And Dan, why don't you?
Yes.
Although I guess folks may still remember you from this morning.
Yeah, so for those that didn't hear this morning, so my name is Donald Raab. I'm I guess, a few things like Java champion, also the creator of a framework called Eclipse Collections, which is an open source collections library that's managed at the Eclipse Foundation. I'd also been on JSR 335 expert group with Vlad and Brian Getz and others. I had also served on the JCP executive committee for quite a few years for two different banks. So, and I think, yeah, it's about the same time doing Java. I started learning Java in 1997, have been programming in it professionally since 2000, 2001. So, yeah, and that's it. I'll let Vlad get started. So.
Yeah. All right, so we did mention that data frames work especially well in the context of data-oriented programming, but it would be helpful, I guess, if we defined what that means. And we will talk a little bit about data-oriented programming, but I guarantee that we're not going to do justice to this topic. So for that, I refer you to the articles you see on the slides. There are blogs that go deep into what, why, when, how of data-oriented programming. But we will use this definition here by Brian Getz, the architect of Java language. Data-oriented programming encourages us to model data as immutable data and keep the code that embodies the business logic of how we act on that data separately. And it's a little bit different than paradigms we usually associate with Java, like object-oriented programming. So it would be helpful if we could compare and contrast object-oriented programming with data-oriented programming. And the primary difference are in how we treat state and behavior. And when it comes to object-oriented world, we are encouraged to encapsulate everything, hide your state, in fact, hide the fact that there is a state, and access, talk to objects by sending messages to objects and getting responses, right? So you don't really know the implementation. You may not necessarily know which particular class, instance of which particular class you're talking to at runtime, because it's a polymorphism. Whoever you're sending message to, you don't really, you shouldn't care, and then you get a response. And the data that you get back could be coming directly from the object, could be computed, could be coming from some other related object, and so on and so forth. Whereas when it comes to data-oriented programming, you kind of do the opposite, right? You just model your domain as pure state, as collections of properties. They can be properties, fields of your classes. They can be columns in your relational tables. They can be grouped in collections. And then you just expose this data to whoever wants to do whatever with it. And obviously, when you're in this context, you want to keep your data immutable. Otherwise, you can create all kinds of chaos with shared state. And again, obviously, very different approaches. You would pick one or the other based on the context, based on what your goals are. we mentioned it briefly on the slide, but like I said, we're not going to go too deep into it. Look at those blogs if you are new to this topic and you're kind of interested in learning more. So this is pretty abstract. Let's take this comparison and bring it into a concrete domain. And in this case, we are going to use donut shop as a domain. And this is actually the domain we'll be using, the types of entities we'll be using for code examples later in this talk. And let's start with object-oriented donuts. So we have our donut shop. The three main entities are donuts on the menu, which are their names, their prices. We have regular price, discount price. Then we have customers. And the way the shop operates, it ships donuts to the customers. For the purpose of this exercise, to keep things simple, you can only order one type of donut in your order. So the third entity that we have is donut orders that kind of brings together the customers and the donuts. And like I said, when you design your object domain right, when you follow all the right object-oriented design heuristics, you should kind of just speak to the boundary of the objects. And this is what this donut diagram is meant to represent. You only see the boundary. You don't see the state. There may be no state. State is just a useful abstraction that helps us reason about objects. Whereas if we want to do this in the data-oriented world, well, we just have three collections of the respective entities, donuts, customers, orders. And this could be collections of Java records. So one very simple way to implement your data-oriented domain. And then if we want to operate on these entities, we just write a function that does it. So for example, here is a function that finds top 3 bestsellers based on the number of donuts. And it uses streams with collectors. And it takes a list of order records as an input and produces the list of bestsellers. So it's nice, fluent code. And we are doing data-oriented programming in Java already. So in fact, as I'm sure you know and you heard during the conference, Java has been adding more and more features that support this data-oriented programming approach. Record seal classes, pattern matching, just some of them. And these are great features, but these language elements do carry some cost. And one is memory overhead. So it costs you to just have an object in memory, which if you're dealing with donut example you saw may not be material, but in real life applications at scale where you have millions or billions of entities, these costs really add up. Also, I mentioned that this code here, it's nice, clean, uses streams, but it's not like instantly obvious what it does. You have to parse and figure out collectors. And there is kind of quite a bit of stuff goes on. So it probably could be simplified, streamlined. And also, in this case, we're using records. And records are still classes. So if you're in an environment where your domain changes a lot, let's say you're just in the experimental phase of your application, or you may not even own the domain, right? Somebody publishes data that you have to consume, and that can change. There is some brittleness to having to continuously refactor it. And Java also supports map-oriented programming, where you represent your domain as maps of maps of maps. It's terrible. Please don't do it. So we're not going to talk about it. But Let's kind of add a data frame to this picture. And what is a data frame? Well, it's just a data structure. It's a tabular data structure similar to a database table or an Excel spreadsheet. And the key here is, unlike, let's say, a two-dimensional array, columns could be of different data types. So like I said, yeah, similar to a relational table. And you can operate it programmatically. So you can take it, plug it directly into your application code. So what's so great about data frames? Well, as we'll hopefully see from the examples, it's more user-friendly and it operates at a higher level of abstraction than collections and operating with, I guess, records on streams and collectors and gatherers and so on and so forth. You also can optimize a lot under the covers. So as a developer, you don't have to worry finding some high-performance collections framework that could be more optimized than JDK collections. You can take advantage of things like object pooling, again, just happening without you having to worry about it. And examples we're going to see, they're real-life libraries used in production applications for use cases like data transformation, data enrichment, reconciliation, data science, data validation, and so on. OK, so let's look at some code. And the first example we're going to look at is the 1 billion row challenge. Who here heard of the 1 billion row challenge? OK, I'd say 50%. So check it out. It's a lot of fun, I guess, educational fun. But yeah, so the 1 billion row challenge was kicked off by Gunnar Morling. This is his interwebs coordinate. It ran through January 2024. And the goal was to see how quickly a pure Java program can process large quantity of data, in this case, 1 billion rows. So here is the challenge from the blog that announced it. Your mission is to write a Java program for retrieving temperature measurement values from a text file and calculate minimum, average, and maximum temperature per weather station. There is just one caveat. The file has 1 billion rows. So when you actually generate test data, it ends up being about 13 gigs of data. So yeah, so these are the links to the blog and to the results. Obviously, folks submitted a lot of solutions. Most of them in Java, and then it kind of spilled into other languages. And the reason we're talking about this is not because we're hoping to win the challenge. It's because it's a classic data-oriented programming problem. So it would be good to see how well data frameworks perform in this context, but also how easy it is to write and read the code. So and that's actually a very important point. So before we jump into the code, let's take a quick survey of the existing solutions. And if you look at the results, they are pretty impressive. So the top 3 results finished the challenge in about 1.5 seconds. And if you look at those submissions, what you'll see is that they have a lot in common. Each one is many hundreds of lines of fairly well-factored code. They use things like vector APIs, low-level APIs, latest language features, latest VM features, some really weird and wonderful stuff that you wouldn't normally think to use in your production, I don't know, accounting application. Accounting could be quite hard. I don't know why I'm dissing accounting.
We wrote a lot of code like that.
Yeah. But if you look at it, it's not obvious how algorithm works. You really have to like scan and parse it. It's also not obvious what it actually does. Like, I mean, OK, you know when you're looking at it that it solves the 1 billion row challenge. But had you not known it, it wouldn't be obvious from like few screenfuls of code what it's trying to accomplish. And it did take a lot of developer time to read and write it, because people kept submitting and resubmitting, trying to squeeze every extra CPU cycle of the performance. And that makes a lot of sense, because it's the nature of the challenge. It doesn't make this code bad, and it kind of calls for these kinds of sacrifices. But what if we slightly or completely change the framing, right? What if we said, instead of trying to squeeze every CPU cycle, we value developer cycles more, right? We value time to market and code readability and code maintainability more than absolute cutting edge performance. And we'll get something out, and it will work, and then we'll optimize it if and when needed. And with that, let's bring DataFrames into the picture. So as we go through code examples, I'll be using this very abbreviated version of the file. So it's exactly the file layout from the 1 billion row challenge. But everything you're going to see will also work with the file that has 1 billion rows. But this way, you can kind of follow what's happening. And we break problem into 3 fairly obvious steps. We load data from the file, we do aggregation and sorting, and then we show the results on the console. And for this part, we'll look at 4 data frame frameworks. One is Python Pandas, which, well, it's not obviously a pure Java framework, but this is what probably people think when they hear the words data frame. This is sort of the quote-unquote industry standard when it comes to data frames. So it would be interesting to see how well it works, what the code looks like, how it performs, to set the baseline and to compare JVM implementations to it. We'll look at Dataframe-EC, which is a data frame based on Eclipse Collections. And we'll talk a little bit more about how it takes advantage of various features of Eclipse Collections. And disclaimer, I'm the creator and a developer for Dataframe-EC. We also look at Tablesaw, which is another popular pure Java data frame implementation. And we will look at Kotlin data frame. So Kotlin is a JVM language. It's available to Java developers. A lot of people seem to be intrigued by Kotlin. So we felt it makes sense to add it to the comparison. All right, so to start with Python Pandas, we load the data. So again, I may have mentioned that, but the code that we're looking is available on GitHub. There will be a link to the repo with all the examples and more at the end of the presentation. So you can take a picture or QR code, whatever. Right, so we just call read CSV function from the Pandas library. The file here is just a variable that contains the file name. The separator, so again, named parameters make it very easy. If Brian were here, I would troll him and ask him when can we have those in Java, but he's not, so I'll skip that. So you have separator as a semicolon. There is no header in the file. There are 2 columns, weather station and temperature. And engine is just an optimized engine which works faster than the default engine. And you have a data frame here. So Very, very nice, easy to read, easy to write, because you can see like all these parameters. Now, group by and aggregation. So we want results to be sorted by the name of the station so that they come out in a kind of consistent way. In Pandas, there are two ways to do group by. One, which will do group by and sorting, and the other one, which will do group by without sorting, and then you have to do sorting separately. Documentation claims that splitting group by and sorting may result in faster performance. I haven't really seen any performance difference, but since they mention it, I figured I'll show both options. So another thing to call out is that when you do disaggregation, you get hierarchical columns, so the table looks like that. Actually, the data frame looks like that, like what you see on the slide. And to produce output, it's pretty straightforward. Like one thing we do is we drop a level of column hierarchy, which makes it easier to iterate. But then we just use standard Python iterator approach. And in this case, index is just the first column, and we call the print function, and here where. And that's what you see on the console. Now let's move to JVM examples. So we'll start with Dataframe-EC. Again, the code looks pretty straightforward. We describe the file layout. So the file has two columns, one of type string, station, one of type float. The separator, there is no header. So again, while it doesn't have named parameters, you have this builder pattern that kind of achieves the same result. Then you create dataset object that links together the physical location of the file and the schema, and you load that file based on the schema as a data frame, and here you have the data frame. Aggregation is also pretty straightforward. So the aggregate function takes two parameters. The list of aggregation functions, aggregators, and they specify the column to aggregate and the name of the result column. And the second parameter is a list of columns to group by. And then you sort. So just want to spend a few seconds on this immutable business. We'll talk a little bit more about it, but for now, like we said, Dataframe-EC is based on Eclipse Collection framework, and it exposes Eclipse Collection data types in its API. Eclipse Collection has types that basically fully compatible with JDK collections, so it's a drop-in replacement for that. But it also introduces a number of collections that do not exist in JDK, including things like primitive collections or immutable collections. So in this case, immutable just simply gives you a factory that creates immutable collections. OK, and to print it on the console, we use like normal kind of classic for each iterator, which takes as a parameter a lambda that takes a row in the data frame. And here we just call printf on the columns within that row, and we get it out on the console. Now, if you look at Tablesaw, it actually looks very similar. Same idea. You describe the file layout. You load it. So in Tablesaw, the data frame type is called table. So you see table measurements. You load it there. The difference being that you can't specify columns in your descriptor. So we set column names after we load the data. Processing is, again, very similar. Not going to spend much time on this. The only difference is, again, you don't get to name columns. Column names are provided for you. And the output follows the same for each pattern here. So when you look at it, you kind of can't help but wonder, does it mean that all the Java data frame frameworks look the same? And the answer is no. And later we'll see examples where different API choices, different implementation choices result in very different looking code. And finally, Kotlin. So this is loading a Kotlin data frame using their data frame library. So this part should be pretty straightforward and kind of looks like the previous ones, so we're going to skip it. The processing bit looks a bit interesting. So a couple of things to call out. First of all, what looks like it's part of language grammar, like this whole aggregate into. For folks not familiar with Kotlin, that's actually Kotlin feature for writing, I guess, DSLs, if you will. So into is an infix function, and it has two parameters, one on the left, one on the right. But yeah, so it lets you do these things in the language, which look like, again, it's baked in the grammar, but it's actually part of this library. And another thing that's interesting is that when you do group by, it will actually create a data frame of data frames, which we tried to show on this diagram, which is an interesting choice and obviously results in more memory used, which could be material. Anyway, the output, same exact for each pattern, and then it just prints the row. So not going to go deep into it. Now, let's look at the performance. And so the first slide shows performance for 100 million row challenge. And the reason we had to introduce 100 million row challenge is because Kotlin didn't really complete the 1 billion row challenge. But we still wanted to have some comparison, and so we kind of went with this. The way to read this graph, you see performance, and performance in milliseconds broken into two steps: load data in green and aggregate and sort and whatever in yellow. And then we also show heap size in purple. Well, for Pandas, it's actually the size of the process in the operating system. But again, it should be a good point for comparison. And the shorter the performance bars, the faster it ran. The shorter the memory bars, less memory it used. So shorter means better. So let's look at the actual 1 billion row challenge. And one thing here, so the pure Java frameworks, there are two sets of results. So we wanted to see how they perform under moderate pressure. So we did tests with 16 gigs and 32 gigs of RAM. All right, so what can we get out of these results? One, Python Pandas does really, really well when it comes to execution speed. And then when it comes to memory, it does very poorly, but that's sort of a known problem with Pandas. So yeah, that's something that's, from what I understand, just there and not going to get fixed. Comparing Tablesaw and Dataframe-EC, Tablesaw does better when it comes to loading data. But both frameworks really benefit when it comes to memory usage from relying on the underlying efficient collection libraries. So Tablesaw relies on fastUtil, and Dataframe-EC relies on Eclipse Collections. And all the, these columnar data structures are actually proxying the respective collections. And that actually may be a problem with Kotlin, because when you look at Kotlin collections, when you look at their data frame and underlying data structures, they just proxy JDK collections, which are not really optimized to operate at this scale. So another thing is, while Tablesaw does well when it comes to loading data, it actually does very poorly when it comes to aggregating the data, to the extent that Dataframe-EC ends up being twice as performant. And my theory is that because it relies on Apache Commons for its math stuff, and Apache Commons is also known to be not the most well-optimized library. All right. So a little bit about Dataframe-EC. One thing, and we'll see what impact it has. One thing to call out is the expression DSL that used to define computed columns, filters, and other sort of custom expressions. And this is different from other frameworks that use internal DSL, which is Java. So we'll see how that kind of impacts the code that you write. You can extend a DSL function and aggregation function at runtime. You don't have to touch the framework itself. And again, which really matters in real-life scenarios, there is a lot of flexibility for dealing with nulls. Again, like it's not maybe purist computer sciencey view that null and null is null and null is poisonous. Unfortunately, a lot of legacy workflows, enterprise workflows, have their own ways of interpreting what null means, and you kind of have to accommodate that. And like I said, it really takes advantage of the Eclipse Collection framework. And with that, I'll hand it over to Dan. He can talk about what that means.
OK. You can all hear me, right? OK, so I think I'm here to answer two questions. One, am I going to just stand up there with my T-shirt looking nice? No, I'm actually going to talk. The other question is, what happens when you bring a collections framework developer to a data frame fight? And the answer is like, well, I'm going to explain, for one specific data frame, how collections actually are a key component of that, right? So we're not comparing collections libraries, to how to implement, the billion row challenge, but I'm going to talk about how collections become a key component. And if you were to sit down and try and implement a data frame, how they can help you. And as Vlad mentioned, Dataframe-EC uses Eclipse Collections. Tablesaw uses FastUtil. Specifically, it's got a set of primitive collections and whatnot. Eclipse Collections, I guess, provides optimized data types. It provides primitive collections. It has a rich API, and Vlad, for his Dataframe-EC library, is leveraging a lot of that. So it was nice also as an open source developer. Dataframe-EC is open source. Eclipse Collections is open source. It's nice that open source developers are collaborating together to work on building things, not just always competing, but building one thing out of another. So I thought that was kind of neat. Just down arrow or?
Space.
OK. So one interesting thing, I used to talk about Eclipse Collections in terms of these 10 different features that you could find in it. And the library is over 1 million lines of code. And what was interesting looking at Dataframe-EC is, of these features, how many of them does Dataframe-EC actually leverage? Because a lot of times, if you're building a smallish application, you may only need 1 or 2 collection types. Vlad's building a data frame library. He needs a lot of stuff. And what you can see is he's actually, wherever you see a green check mark, Vlad's actually using something from there, right? So 8 out of the 10 things that are available in Eclipse Collections, he's using them. So, which is quite nice to see that level of usage from the library. So congrats on being able to use all that.
Well, thank you.
You're welcome. So looking at, I guess we're going to look at Eclipse Collections types. And if we look at DataFrame itself, right, you're looking at a bunch of columns. And I think of, Vlad mentioned like DataFrame, you can think of it as a table or a spreadsheet. I think of it as it's a columnar data store. Right, and a lot of times we think of data as having rows and then columns. I look at data frames as like having columns and then rows, right? And if we broke down the data frame into its component parts, what we see is that there are columns, and like we have, let's say, columns that contain strings, columns that contain dates, and then maybe columns that contain numbers. And on this slide here, what you see is there are different types that are being used behind the scenes. Now, one of the interesting things, if you've got a lot of data, and Vlad and I both come from a financial services background, so we're used to using things like positions and accounts and products, and what you get in that space is you may have a lot of positions or transactions, accounts and products that are a lot smaller. So we're used to using techniques like pooling, which basically makes sure in memory we only have a smaller number of unique things. And one of the first things you can see on the slide to the left is that for the customer column, the data, once it gets loaded, actually gets pooled. So for this particular 1 billion row challenge, if you were reading in 1 billion strings out of a CSV file, that's going to take up a lot of memory, right? By using pooling, what you can do is just unique down, because there's a much smaller number of the, was it weather stations, right?
Yeah, 413.
Yeah, 413 out of a billion, right? So compressing that's quite good. So there is a type in Eclipse Collections called pool. It turns out our hash set is a pool. So we have a class called unified set. And what it means is if you've ever looked on the set interface in Java and looked for a get method, it doesn't exist. If you look on unified set, it actually has a get method, and it's because it implements the pool interface. And what it does is like you say like, hey, pool, get me this thing, and it basically, if it already has it, it gives you back the unique thing. So what you can do is let go of your thing, and it gets eligible for garbage collection, thus allowing you to unique. So most people will typically use a map for this purpose, like have a key and a value. A pool is a set. It's like I look something up, if it's in there, I get that back, right? So next thing you'll see is like for the numeric data, right? So for quantity, Vlad's actually using for Dataframe-EC a mutable int list. And a mutable int list, behind the scenes is just going to be a list that actually has an int array. So if you heard, talking about Valhalla and stuff and value types coming, this is actually a primitive list. So you get great compression. You're also going to get great performance when either iterating over it, doing operations like summing and whatnot. So going to take less memory and do things faster. Now, what's interesting was once you deal with primitives, though, you have this problem of, well, it's both a problem and not a problem, mostly not a problem. You don't have nulls, right? There's no null problem, unless you need nulls. Where when the data's coming in, if you need it to represent a null, and Vlad, in order to do this, is actually using a mutable Boolean list to keep track of all the indexes when he's reading them in then are potentially null. And if you look at the last row, that's actually containing a null value. So that's being flagged as a 1. So he has a way of actually representing if the data is supposed to be null or not. Then you've got, obviously, double values represented via mutable double list, also a primitive collection, going to get the nice compression and performance benefits. He's using a mutable Boolean list so that you can actually flag individual rows. So you can see like where there are, I guess they're ones are the ones that are being selected. You can actually say select these rows, and the mutable Boolean list will allow you then to just filter those rows out by the indices. Last thing is, if you wanted to index this structure, so Vlad's using a mutable map with a list iterable. So you can basically say index on one column or multiple columns, and that's the list iterable that gets passed in. And then, you're then going to actually have int list of the indices of those rows. So if you look over on the right, that table there has, it's being indexed by the customer. So we see that we have Alice has 5 rows, 0, 1, 3, 4, 7. Bob 2, 9, Carol 5, 8, and so on and so forth. So this is kind of, once again, showing you underneath the covers, collections are actually being used, right? So while we're not looking at, once again, collections versus data frames, you don't really need to look at that. Collections are a component of data frames here. So I'm going to go real quickly. What Vlad, we talked about earlier in the slides is that Eclipse Collections and Dataframe-EC actually share a lot in terms of the terminology and the naming of things, right? So you can see like Eclipse Collections has a partition method, which will basically split a data set based on some predicate, right? So either things included or excluded. Same thing with Dataframe-EC, also named partition. Eclipse Collections, Dataframe-EC both have a distinct method, which would basically give you effectively like the uniquing of things. So, select is filter. I love that Dataframe-EC includes select by, and I guess this is using the mini DSL you have, right, for actually doing the filtering. But yeah, select means filter. It's an inclusive filter. Eclipse Collections supports both inclusive and exclusive. Select is inclusive, reject is exclusive. I talk about all this in the book if anybody's interested. But I think, do you have reject as well?
No, but there is partition.
Okay. Well, then, yeah. Well, that's doing both then. And then, sorting. But then I'm going to hand it back to Vlad. So thank you.
OK. So we have about 5 minutes. We'll go through more interesting functional examples. And we're going back to our donut domain. So we have 3 data frames in this case, representing our 3 main entities as collections of columns. And we will look at these 4 use cases. So list donuts in popularity order, similar to that function example that we saw earlier. Priority orders for tomorrow. Somewhat arbitrarily, I define priority orders as large orders or orders that are going to Bob, one of the clients. Total spend per customer, so just simply a list of customers and how much money they spent. And donut count per customer per day will show us how to use pivot functionality with data frames. For this portion, we focus on just pure Java data frames. So we'll compare and contrast Dataframe-EC and Tablesaw. But like I said, in the repo, you'll see examples for the other frameworks as well. So actually not going to spend much time on donuts in popularity order. Aggregate by works exactly like what we saw before. Sort, the only difference here is that we sort by 2 columns, one in descending order, one in ascending. So we sort by donut name just so that we break ties when there are 2 donuts with the same quantity. And the last one, keep columns, because we only care about donuts and we don't care about the quantities. We drop all the columns and just keep the donut column. For Tablesaw, visually, functionally, it all looks very similar. The only difference is how you indicate sort direction, and that's pretty much it. OK, now, priority orders for tomorrow. So this is where this DSL difference comes in. There is a select by method, which you already saw. And this is the external DSL. So there is this grammar that basically just invented for this framework. But if you look at it, you will immediately see what's happening here. So tomorrow is just a local date that represents tomorrow. But as far as this language goes, you can read it right away. I'm pretty sure of that. And with some trivial amount of effort, you can write it, probably like with no effort at all. That gives you back a data frame. If you look at how you do this with Tablesaw, that uses internal DSL. So again, it's declarative, where method is equivalent of Dataframe-EC select. But it's like there is a lot of text. Now, the text is mostly Java. So if you type something wrong, maybe the IDE will give you like a red squiggly. You still have to write tests for all the obvious reasons. And you still have strings here. So you could have typos in these strings where IDE wouldn't really catch them. So again, I would argue from reading and writing code perspective, figuring this out is kind of harder than having an external DSL.
We're at
yep.
45, so do you want
OK, 2 more minutes. Well, they're starting the fire at the fireplace. So, OK, total spend per customer. So to calculate a dollar amount of each order, we again, helps to think as if we were in the relational universe, right? We join donuts to orders to get donut prices. And then we compute order amount based on the order size. We use regular price for small orders. We use discount price for larger orders. And then group by and add up. So join to get individual donut prices. Joining is very straightforward. You basically specify the column to join by. And for Dataframe-EC, you can specify which columns you want from the data frame you're joining to. And what you end up with is a data frame you see on the bottom with 2 extra columns shown in green. Now, if you want to add a computed column, well, again, you use this DSL, which I would argue fairly natural, at least for folks in this room. And you add a column. You notice that we don't specify a column type because everything is actually strongly typed behind the scenes. And the type of the column is the type of this expression. So type inference and type validation is done for you. And you end up with a data frame with this computed column shown in yellow. When you do this with Tablesaw, again, you use internal DSL. So it's all Java. You create a column. You use this declarative code to populate the values in the column. And again, you can look at it. You can figure out what's happening. But it's a lot of text to express this. And also, it's impossible to externalize it, right? So for example, let's say this is a business rule, and you want a business person to own this, right? You don't want them to go into your Java code and check in and deploy the Java application. You want this to be maybe in the UI or in the configuration file. And that's kind of impossible with internal DSL in Java. OK, this is just an alternative approach for populating this in Tablesaw. And aggregating and sorting works just like it did on the previous slide, so we'll skip that. Pivot, that just shows you how easy it is to do pivot with data frames. It's similar to a pivot table you would do in Excel. The difference there is that Dataframe-EC has those parameters as lists because it can pivot by multiple columns, and it could use multiple aggregation columns, multiple pivot values. Tablesaw limits you to 1 each, but for the purpose of this exercise, it works just fine. All right, and yeah, so takeaways. Java data frames are out there. They can be a useful addition to your data manipulation toolkit. They work very well when you, again, deal in a data-oriented sort of context. You have your data. You want to perform operations on this data. They make things like filtering, aggregations, transformations, enrichment easy. Things you would normally do when you experiment with data, maybe you pull up Excel, maybe you pull up Pandas, Jupyter Notebook. But then once you're done with experimentation and you say, OK, now I want to put it in my production application, which is in Java, well, I guess I'll just have to try and rewrite everything I have here in Java. Well, if you're using Java Data Frame to begin with, and some of them support notebooks, then, well, guess what? It just works with your production environment. And yeah, Java Data Frames, as you saw, could be very efficient. So maybe you can give up that Spark cluster.
Hey, the links.
Yeah, and this is the last slide.
It's like we're waiting for the slide.
Yes. Yeah, the talk and the sources are on GitHub. We have links to 3 data frame libraries, 2 of which we covered, and the other one, dflib, is also out there used in production. So, data frames, check them out. You have choices. They're cool. And thank you very much.
Okay.